Hello everyone, my name is Ibrahim Kettaneh, and today I'm going to present FLAIR. It's a novel approach that accelerates read requests in leader-based consensus protocol. This work has been done with the collaboration of Hatem Takruri, Ahmed, and our advisor Al-Kiswany at the University of Waterloo. Modern cloud applications are read-intensive. The read-to-write ratios in some cloud applications reach up to 500 to 1. Moreover, modern cloud applications require data reliability because machine failures should not cause data loss. It's usually achieved using replication, and strongly consistent replication protocols are widely adopted due to their well-known defined semantics. However, these protocols are inefficient for read-heavy workloads, and the main reason is they are leader-based. Here are some examples of leader-based consensus protocols, such as Raft, Zap, and some implementations of Paxos and ViewStamp replication. Leader-based consensus protocols are inefficient because in those protocols, the reader handles both replication as well as serving read requests. And as you can see here, the system is bottlenecked by just one machine, which is the leader. And there is a missed opportunity because, as you can see, followers are not being utilized and they are sitting idle. And the reason is they are not being utilized is they might have stale data. So one of the current approaches is read leases, in which the leader grants a lease to the followers. And during this lease period, followers can serve read requests and the object value will not change. And if the leader needs to change the value because of write request, the leader needs to revoke all the leases and then do replication and then re-grant the leases. And as you can see, there are some drawbacks. It needs a complicated lease management protocol, as well as it increases the write latency because of the lease re-granting and revoking. Also, it complicates the fault tolerance because if a machine fails while owning a lease, the system needs to wait until the lease timeout before it can progress. On the other end of the spectrum, and in order to utilize followers without having those leases drawbacks, some people ditched strong consistency altogether, and they went with eventual consistency, in which replicas can serve read requests, albeit the possibility of returning stale data. And we asked ourselves a question: can we utilize followers without sacrificing consistency and without having leases drawbacks? And the answer is yes. We present FLAIR. FLAIR is a novel approach that utilizes followers and allows them to serve read requests while maintaining linearizability. FLAIR is not restricted to any specific protocol. As a matter of fact, it works on top of modern leader-based consensus protocols. The main idea in FLAIR is that the network detects read-write conflicts and load balances reads across those consistent replicas. The key enabler here is the new added programmability in network devices. So, how does FLAIR achieve this? In FLAIR, the network switches monitor write requests and responses and can identify which objects are stable and on which replicas. And then it can load balance reads across those consistent replicas. So, in a nutshell, FLAIR is an in-network, consistency-aware load balancing protocol. We implemented FLAIR and we evaluated it in a cluster with Barefoot Tofino switch. And in the evaluation, FLAIR achieves between 1.4 to 2.1 times higher throughput and between 1.5 to 2.4 times lower latency than other approaches. In this talk, I will start with an overview about programmable switches. I will talk about FLAIR design and implementation, and I will conclude with an evaluation of FLAIR against other systems. Let me show you a simple key-based example in programmable switches. In this example, let's assume that we have two nodes. Each of them is responsible for a specific key range. And what we would like to have is for the programmable switch, based on a custom header, let's say here, for example, a key, based on this custom header to forward this request to one of these two nodes based on the value of it. In this case, the key is 200, so it will forward it to node 1 because it falls in its key range. We can achieve this by adding one pipeline stage. For example, after layer 2 and layer 3, we can have our pipeline stage. that contains multiple match plus action tables. In this case, for example, we can match on our custom key in the packet header. If it's in a certain key range, we can perform an action. And if it's in another key range, we can perform another action. Actions are programmable. By the way, everything here is programmable using one of the packet processing programming languages, such as P4. In this example, we are setting the destination IP address to one of the IP addresses stored in the switch memory. So, in this technology, programmers can at pipeline stages, they can match on custom packet headers, they can program different actions, and packets can change switch memory, everything happening at line rate. So as you can see, this is a very powerful tool that could allow for the network to accelerate different kinds of applications. However, there are some challenges. Programmable switches need to process packets at line rate, which means that there are a lot of restrictions added to this technology. For example, it doesn't support loops or recursion. As a matter of fact, it has a very restricted pipeline-based programming model with a very limited number of stages. Also, it has a limited computational power and a restricted memory access model. And the question is, can we use this technology, despite these challenges, in order to allow for the network to identify which objects are stable and forward reads to those replicas? This diagram shows FLAIR design. In this diagram, let's assume that we have one leader and two followers. And as we mentioned earlier, FLAIR works on top of leader-based consensus protocol. So in this diagram, all of these replicas are actually running FLAIR module on top of them. FLAIR requires a programmable switch that is running FLAIR pipeline. Also, FLAIR requires a network controller that steers FLAIR's packet into this programmable switch. So in FLAIR, clients send read requests, and the switch will identify which replicas can serve this read request while maintaining linearizability. In this case, for example, let's say follower 2 is one of these replicas, so it will forward it to him. And now the question is, how can the switch identify which objects are stable and in which replicas? And the answer is in what we call the object stability array. This is a data structure that is stored in the switch. In this data structure, keys are partitioned into many ranges. And for each key range, there is a status that is either stable or unstable. If the status is stable, it means that the switch knows which replicas are consistent with the leader. In the first key range, for example, the stable replicas are the leader and follower 1. And in the second key range, all of the replicas are actually stable. However, as you can see in the third key range, it's marked as unstable, which means that the switch doesn't know which replicas are consistent with the leader. So, to put all of this together, let's have this example where we have one leader and two followers. And let's say that we have in the system key 5000 with value A. And this value is replicated and consistent on all replicas. And the object stability array in the switch, all of the key ranges in it are stable and on all replicas. So, the client sends a read request. The switch will check this key range, and in this case, it's stable on all replicas, so this read request could be forwarded to any of the replicas. In this case, for example, it's forwarded to follower 1, and it responds back to the switch. The switch will perform some extra checking and will forward it back to the client. Now, let's assume that the client will need to change the value from A to B. The switch will mark this key range as unstable and will forward the write request to the leader. And now let's assume before the leader, for example, start processing this write request, another read request arrived at the switch. This key range is now unstable, which means the switch doesn't exactly know which replicas are consistent with the leader. So in FLAIR, we perform the safe choice, and we forward this read request to the leader. And the leader will respond back with the correct value, and it will be sent back to the client. And now, let's say that the leader will start replicating this write request. And for example, only follower 1 acknowledges back to the switch. So as you can see here, now, value B is actually committed because it's on majority. However, follower 2 is actually stale because it didn't apply this new change yet. The leader knows this information and will forward it back to the switch. Now, the switch will mark this key range as stable. However, it's stable only on the leader and follower one. When future read requests arrive at the switch, it will perform the same check, and now it can be forwarded to any of these two stable replicas. As a matter of fact, future read requests will be load balanced across those two replicas. FLAIR is a complete protocol. It handles concurrent writes to the same object, packet reordering, and all different kinds of failures, as well as network partitioning. We validated FLAIR, and we have a detailed proof and a TLA plus model checking. In this talk, I will only focus about how FLAIR handles concurrent writes to the same object. However, all those details can be found in the paper. So let's assume the x-axis shows the time at the switch. And this black line shows the time from which the write request arrives at the switch until the write response arrives back at the switch. And during this time, let's assume that there is another concurrent write 2 in this example, to the same key. What we do not want to happen is for the write 1 response to change the object stability array, because there is a concurrent write that might have different stable replicas. So in FLAIR, we perform the safe decision, and we mark all this time of interleaving writes with the same key as unstable. FLAIR achieves this by assigning a unique sequence number for each write request. And the object stability array stores the sequence number of the last write. So in this example, write 2 came after write 1, which means that the object stability array for this key range will have write 2 sequence number. And this key range will remain unstable until the last write, which is write 2, response comes back at the switch. In order to evaluate FLAIR, we implemented FlairKV, which is a key value store that is built on top of Raft, which uses FLAIR. We implemented the programmable switch using P4 language, and it utilized 12 registers and 30 tables. And that only used 5% of the switch memory, leaving plenty of space for different kinds of applications. Also, FLAIR facilitated implementing different types of load balancing techniques. More information about these can be found in the paper. We compared against different alternatives. We compared against leader-based, such as Raft and ViewStamp replication, and against an optimization called leader leases, and we call it optimized Rafts. And we also compared against unreplicated system, which means that there is no replication, and this should show the best possible performance of leader-based consensus protocol, as there is no replication overhead. And we evaluated against fast Paxos and the follower leases optimization that we mentioned in the beginning of the presentation, and we call it F-leases. We have different metrics such as throughput, latency, and our efficiency load balancing technique, and we use different types of workloads. However, in this talk, I will focus talking about the throughput and the latency of our evaluation. So, to show the throughput, the x-axis shows the number of clients, while the y-axis shows the throughput in terms of thousands of operations per second. By the way, the workload that is used here is a uniform workload B from Yahoo benchmark, which have 95% of reads. As you can see in the figure, Raft, Fast Paxos, and ViewStamp replication achieve around 60,000 operations per second, while optimized Raft achieves up to 200,000 operations per second, and unreplicated achieves even better than this at around 250,000 operations per second. And as we mentioned earlier, this shows the best possible performance of a leader-based consensus protocol. And this is the performance of F-leases. And as you can see, it achieves even better than this because it now can utilize the followers to serve read requests. And this is the throughput of FlairKV. And as you can see in the figure, it has up to 42% higher throughput than F-leases and up to 2.1 times higher throughput than optimized Raft. Next, I will show the read latency. This figure is a CDF for the read latency for the same workload, that is workload B Yahoo benchmark. The x-axis shows the latency in terms of microseconds, while the y-axis is the fraction of reads, because this is a CDF. And as you can see, unreplicated system as well as optimized Raft have a really similar read latency, because in both of these systems, leaders can immediately serve read requests without contacting other replicas. And this is the read latency for FLAIRs. And as you can see, it achieves better latency because now the system is not bottlenecked by the leader, and now it can utilize the followers. However, as you can see in the tail latency, it performs worse than other approaches because of the complexity of lease management. And this is the read latency for FLAIR. And as you can see, FLAIR achieves better than all of other systems because it utilizes the followers as well as it doesn't have complicated lease management protocols. FLAIR achieves up to 50% lower latency than FLAIRs. And this is kind of fascinating. So we dig deeper into it. And we found two main reasons why FLAIR achieves lower latency by 50%. The first reason is in FLAIR, we avoid inconsistent replicas. However, in FLAIRs, clients send read requests to followers that might or might not have a lease, and this could add extra latency. And the second reason is in FLAIR, we implemented a load balancing technique. We call it avoid the leader, which avoids the leader if there is a lot of writes in the system, which is something that cannot be implemented in FLAIRs. So, in the end, FLAIR is a shim layer that works on top of current leader-based consensus protocols that exploits programmable switches and allows followers to serve read requests while maintaining linearizability. FLAIR achieves 2.1 times higher throughput than classical approaches and 1.4 times higher throughput than leases. And FLAIR achieves 2.4 times lower latency and up to 1.5 times lower latency than FLAIRs. So, the main takeaway from this talk is, despite their limitations, programmable switches can be leveraged in order to accelerate complex system protocols. Thank you very much, and if you have any questions, feel free to ask them.
Hello, this is Danny Chen from Princeton University. As we all know, consistency protocols are used to improve reliability of the system and tolerate crashes. So apparently, if we want to tolerate crashes for the switch, we probably need more than one switches. So can you give some insight on what should we do if we're using 3 switches or 2 switches in this case? Should we forward all the write requests through all 3 switches before sending to a leader?
That's a great question. So in FLAIR, we actually, FLAIR can actually, it handles switch failures easily. More information about this can be found in the paper. It has like a whole dedicated protocol to this. It adds session number and yeah, we can definitely talk after this.
Okay, and second question is, I see that you're using session numbers and sequence numbers, etc. So if a message gets dropped, maybe one session number never get feedback. So in that case, will you lose liveness?
Not really. So FLAIR's liveness is really dependent on the underlying protocol. So if we are using, for example, Raft and Raft have liveness, so FLAIR will have liveness too.
Even if a packet gets dropped from the leader to the switch?
I mean, it depends. Like if it's a read request, for example, the client will time out and it will send the read request again. And if it's a write request, the client will time out and will resend the write request to the switch.
Okay, let's talk offline.
Sure.
One more question.
Question, Chun from Future Way. Question is in the case that I don't want to introduce a single point of failure, how do you think that we can sync up the table? Because this table is dynamic now, the table.
Sorry, which kind of tables, sorry?
The array.
Oh yeah, sure. So yes, FLAIR is not single point of failure because it can handle switch failures easily. We have hot switches that if a switch fails, the leader will update the new switch with the object stability array. And it doesn't take that much time. And yeah, it's not a single point of failure. Don't worry.
Let's thank our speaker again.